This is Dr. Pratima, Faculty in Physics, Institute of Aeronautical Engineering, Hyderabad. Glad to see you now as we have finished the Module 3, Part 1 and Part 2. Let's now do a bit of some numericals so that we can understand the subject in applying the mathematical concepts. First, if you see the numericals of lasers, which is the Part 1 of Module 3, we will be solving it by using the formulae which we have learnt in the Module 1. The first problem, if you see, calculate the wavelength of the emitted radiation from a semiconductor diode laser which has a band gap of 1.44 electron volt. So though semiconductor diode laser was not there in the curriculum for us, we are just trying to understand how the wavelength varies when the light is made to pass through a semiconductor with certain band gap. So here what is given for you is the band gap Eg. We know that E is equal to h nu, where nu is equal to c by lambda. So you get it as h into c by lambda. So what you need is lambda. So lambda will be given as hc by E, where this E is the Eg. E was our energy actually. And this energy is the energy which is needed for the absorption to take place from when the atom goes from the lower energy level to the higher energy level, and which is the primary step for the emission, the stimulated emission to happen when the atom decedes from the metastable state. So now what do you have here? You are given the Eg, you know h, and you know c. Just substitute all of them here. But one thing you have to understand here is the energy gap. The energy gap is given as 1.44 electron volt, whereas h is in joules. And we know how to convert the electron volt into joules. If 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules, then how much is 1.44 electron volt? How many joules is it? We know that it is 1.44 into 1.6 into 10 to the power of minus 19 joules. So you can substitute that here. And h here. And c, we know that it is 3 into 10 to the power of 8 meters per second. You will end up in the answer as 8663 angstrom. Coming to the second problem, a semiconductor diode laser has a wavelength of 1.55 micrometer. Find its band gap. So the same formula, but here we have to find out Eg. In electron volt, he is asking in electron volt. Why? Because h is in joules. So just substitute h, the constant what you know, c what you know, the velocity of light, and lambda is given as 1.55 micrometer. So convert it into meter, you get it as 10 to the power of minus 6 meter. So substitute all of them here and you get it in joules, and whatever answer you get here, you just convert it into electron volt using this conversion, standard of conversion. 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules. So, for suppose if you want me to do for you, so what do you get? If I take it as 6.63 into 10 to the power of minus 34 into 3 into 10 to the power of 8 by lambda is 1.55 into 10 to the power of minus 6. If you want, so this is in joules. So normally if you want to calculate now, you can get the answer and you can convert it into electron volt. Or else if you want to do it now itself, then you have to take it like 6.63. Yeah, if I write here itself 1.6 into 10 to the power of minus 19, and this turns up to be electron volt. So the answer will be 0.8 electron volt. The third problem, calculate the wavelength of emitted radiation from a semiconductor diode laser which has a band gap. So again, you are given the band gap Eg in electron volt, and you have H here in joules. So it's better if you convert the electron volt into joules so that it will be easy for you in the beginning itself. So band gap Eg is given as 1.68 electron volt. So if 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules, 1.68 electron volts is equal to how many joules? So it will be 1.68 into 1.6 into 10 to the power of minus 19 joules. So if you can substitute this Eg in joules here, you get lambda is equal to 6.626 or 6.363 into 10 to the power of minus 34 joules seconds into 3 into 10 to the power of 8 by 1.68 into 1.6 into 10 to the power of minus 19. So you will end up in 7410 angstrom. The last problem, if a semiconductor diode laser has a wavelength of 1.42 micrometer, find its band gap in electron volt. So the same way, you are given wavelength in 1.42 micrometer, convert it into micrometer, 10 power minus 6 meter, and you can just give it as 6.63 into 10 to the power of minus 34 into 3 into 10 to the power of 8 by lambda is 1.42 into 10 to the power of minus 6. So you end up in getting the answer as 0.087. But it is electron volt. Here you have joules. So whatever you get here, you have to you get it in joules. Please convert this into electron volt using this standard how we have done in our previous problems. So now I want to go into the second part of our third module, which is fiber optics. In fiber optics, we have plenty of formulae where we have seen the numerical aperture and the acceptance angle, where the numerical aperture is given as the sine of the acceptance angle. And the numerical aperture, we have derived the formula as root of n1 square minus n2 square by n0, where n0 is the refractive index of the medium, through which the light passes, propagates, and then enters into the core and the cladding, where n1 is the refractive index of the core, which is always greater than n2, which is the refractive index of cladding. So if we have seen that if you can take the numerical aperture and solve it in terms of the refractive index change, which is delta, which is the ratio of the change in the refractive indices like n1 minus n2 to the refractive index of the core, then you can get refractive index difference, which is related to the numerical aperture, as numerical aperture is equal to n1 times of the square root of 2 times the refractive index change. We have seen it how we get in the previous lecture. Like how do you get it? Numerical aperture is equal to square root of a square minus b square. Here can be written as n1 plus n2 into n1 minus n2 by 1 when you take it in air. And we know that n1 is almost approximated to n2, and if you can take this as 2n1 into n1 minus n2 and you take the square of it, you get it as 2n1 into n1 minus n2, right? So n1 minus n2 from here, you can get it as delta n1. So you end up numerical aperture as n1 into 2 into delta, because this n1 and n1 goes as n1 square. So 2 delta into n1 square. So numerical aperture, if you take the square root, you come out as n1 square will come as n1, and square root of 2 delta will be left. Thus, you get the relation between the numerical aperture and the refractive index change, fractional refractive index change. Using this formula, let's try to solve some problems. Calculate the refractive indices of core and cladding of an optical fiber with a numerical aperture of 0.33 and their fractional differences of refractive indices being 0.02. So here what is given? You are given the numerical aperture, which is 0.33, and the fractional differences of the refractive indices being 0.02. So if you substitute this in this formula, which you know, the relationship between the numerical aperture and the fractional refractive index change, what do you get is 0.33 is equal to n1, which you have to find out, into square root of 2 into delta is 0.02. So if you square this, you get square n1 square, and you can erase this square root. Right? So from this, n1 square can be given as 0.33 square by 2 into 0.02. So from this, you get n1 as 1.65, and we know that delta is equal to n1 minus n2 by n1. And we have 1.65 here, just substitute here. So, and we know delta as 0.02. So 0.02 is equal to 1.65 minus n2 by 1.65. So if you just get it 0.02 into 1.65 is equal to 1.65 minus n2. So with simple algebra, you end up with n2 as 1.617. If you want to check your answers, you can just substitute this n1 and n2 in this and check for the delta, which is given for you as 0.02. So this is how you have to calculate the refractive indices of the core and the cladding when you are given the numerical aperture and the fractional refractive index change. Coming to the second problem, a step index fiber has a numerical aperture of given. The numerical aperture is given as 0.16 and a core refractive index, that is N1, is given as 1.45. Calculate the refractive index of the cladding, that is N2, is equal to how much, and the acceptance angle is equal to how much. So we know that numerical aperture is always the sign of the acceptance angle, but you want the acceptance angle. So the acceptance angle alpha will always be the sine inverse of the numerical aperture. So sine inverse of 0.16. So here there is a small twist. So sine inverse of 0.16, if you have to do in your scientific calculators, what do? You take sine inverse and you give 0.16. You get some answer in the display. Let that answer be like that and press this button, which is given as minutes, degrees, minutes and seconds on your calculators. You find this button. So once you get the answer of sine inverse of 0.16, let that answer be on the display like that and press this button. You will get the answer as 9 12. Maybe it's displayed like this, but in some calculators, but it is 9 degrees 12 minutes. So you should always give the acceptance angle in terms of its angle. So you can't express it in terms of decimals. You have to express it in terms of degrees. So this is how you have to convert your answer, which is in decimals, to degrees. So now you have acceptance angle. One of the answers is found. So now you have the N1 and you have numerical aperture. It's very easy to find out N2. More than that, one thing which you have to observe here is you're not given any medium. We know numerical aperture is square root of N1 square minus N2 square by N0. When you have to consider this formula, you have to look whether N0 is given or not. Suppose in your problem, when you are asked the numerical aperture, the medium is not mentioned. That means the medium is air medium. Take it for granted that the medium is air medium, and in air medium, the refractive index is 1. So for this formula, we are not given any media. So medium of propagation or medium of launching of the launching signal. So the N0 is 1. If N0 is 1, you end up in N1 square minus N2 square as the numerical aperture. And now you have the numerical aperture as 0.16. Square it so that the square root will be cancelled. And N1 square is 1.45 and you want N2 square. Just go for simple algebra and you will end up as N2 as 1.441. So that's how you can end up in the calculation of the acceptance angle and the refractive index of the cladding. Now the third problem is the refractive indices of the core and cladding of a step index fiber are given, and we need to calculate the numerical aperture and the acceptance angle. So what is given? 1.48 is the refractive index of the core and the refractive index of the cladding is 1.45. Be very careful when you are noting it down. Respectively is given, so you should be very careful. Okay. So now the first one is the numerical aperture. We know that here again you are not given any medium. So numerical aperture ends up in root of N1 square minus N2 square because N0 is 1. You are given N1 and N2. Just substitute that. You end up in answer as 0.2965. And the second one, which is the acceptance angle, you know that it is sine inverse of the numerical aperture. So sine inverse of 0.2965, as I have told you, you'll end up in some answer like, and then you just press this button, then you end up in 17 degrees 14 minutes. So always remember that you should mention or you should conclude your acceptance angle not as decimals but as degrees. So now coming to the fourth problem, an optical fiber has a numerical aperture of 0.20 and a cladding refractive index of 1.59. Find the acceptance angle for the fiber in water which has a refractive index of 1.33. So what is given here is the numerical aperture. The numerical aperture is given as 0.20 and a cladding refractive index N2 is given as 1.59 and N0 is given the refractive index of water as 1.33. You need to find out the acceptance angle. So we know that the numerical aperture is equal to square root of N1 square minus N2 square by N0. We have N2, we have N0, we know NA, that is a numerical aperture. Just substitute in them and find out N1. And we know that the acceptance angle is equal to sine inverse of the numerical aperture. Thus, you can get the acceptance angle too. So, from this, you can get 0.20 is equal to square root of N1 square minus 1.59 square by 1.33. From this, you can get N1 substitute back in NA, and then you can get this answer. There is also one more way where the acceptance angle can be written as sine inverse of the numerical aperture by n naught. So if you can take like this sine inverse of 0.20 by 1.33, then you will end up by taking the in degrees minutes as 55.37 minutes. So this is the acceptance angle answer directly. So there are two methods in which you can do this. Coming to the next problem, calculate the fractional index change for a given optical fiber, that is delta. You need to find out if the refractive indices of the core and the cladding. So given, what are given? Core is N1 is equal to 1.563 and N2 is given as 1.493, and we know that the fractional refractive index change is delta is the ratio of the change in the refractive indices to the refractive indices of the core. So you have everything 1.563 minus 1.493 by 1.563. You will end up in the answer 0.0415. So coming, you can even go for some more problems from your textbooks for practice. Hope you have enjoyed the calculations. If you are not able to find out the answers, you can just practice it one more time carefully and you can definitely end up at the answers. Hope I'll see you back in my next class. Bye.
Like, share and subscribe. Hit the bell icon for more updates.